record the sessions to the cloud. Then we move on. Okay, guys, today we are gonna start a new, I should say, a new topic, which is something that it's essentially very distinct to with respect to the trigonometric functions, equations, and geometry, which we covered before. We are going to talk about the infinite sequences and finite sequences. And now, okay, in order to describe what do I mean by a finite sequence, let's talk about that. And it's essentially, this course is going to be much easier than the ones which we covered before. That's why I decided to just put that towards the end of the class. Then you feel that you need some motivation to carry on this session. Because I think you feel very exhausted so far, huh? You've worked so hard. You had lots of new concepts to learn. Now you want something easier, huh? Correct? Okay. Now, look at that. What do I mean by the sequence and what do I mean by the series then? Look at that. For example, I'm just going to guess what I'm trying to write. For example, I say I'm just going to write, for example, 1, 3, 5, 7, 9, 11. And when I reach there at the number 11, I'm just going to make it blank. And I'm going to ask you, for example, if I write the next number, for example, 15, you guess what is that number is going to be? What do you think should I just fill in the square which I have there?
13.
13? That's so true. It becomes 13. Why did you guess 13, Rose? Explain the process of your thought before you just ended up with this answer.
It's all singular. All
I mean, all of
number.
them are odd numbers, huh?
Yes.
Yeah, that's so true. Look at that. You said that. That's so true. Thanks, Rose. You say that this is 1, 3, 5, 7, 9, 11, 13, 15. Then the thing that we just may have in our mind is that we have a pattern that it repeats itself. And the pattern, what do I mean by the pattern? We have two things that we have to we notice here. First of all, we are not working apparently with the functions. The functions, what course do we have right now? The course that we have right now and the thing that we are learning right now is what we call that functions 11. It's apparently, it means that we are working explicitly with the function. It means that we have an input, we have a transformation that it transforms our input to an output that it becomes our, let's say, the range, that the thing that we get the output from the function. Apparently, here, we do not see any function. I emphasize an explicit function because when we look at this, we see a bunch of numbers that they have been ordered from left to right, and they try to tell you something, try to send you a message. They try to send you a message, and the message is that, look at these numbers and try to find the hidden message from there, because that's the thing that we are doing. There is a hidden message for this. The sequences of the numbers, which it is essentially, it has a message. It says that, okay, find what it's going to tell you, because we do not have a function, but we have these numbers in order, and you were able to guess that this number, this blank, is going to be 13 because you identify that pattern. And that pattern, as I said, that's the message. which it tells you that how these numbers is going to be generated from the previous one. For example, you see that in order to get the 13, you needed to start from 11. And from 13, you move off to 15. And from 9, you move to 11. From 7, you move to 9. You see the pattern that from wherever you are, you start from that point to get to the next step. But first of all, you need to define the pattern. And essentially, that's what we define as a sequence of numbers. The numbers which they follow a prescription in order to be generated next. For example, the prescription that you see, you can make a prescription what is going to be the next one after 15, which you say that, okay, I got the hidden message. I got the hidden message from this pattern, from this sequence of numbers, and I expect that I predict that the number over there has to be 17. And essentially, all of this represents a sequence. Then a sequence is an array of the numbers which they follow an order and they have a hidden message. That's how they are generated. And that's how we define a sequence of numbers in functions 11. Any questions, guys?
No.
No. Give me 1 second. I open the window. It's getting too hot in here. Give me 1 second. Okay. Now look at this. That's how we define a sequence of numbers. Then based on the definition of the sequence of numbers, we can identify so far 2 characteristics. The first characteristic is the order that these numbers, they follow. We say that order. They have an order. You see that the numbers, they are not randomly and chaotically generated. You see the comma, we say that they follow from the left to right. And we know that the previous number has to be 7 in order to get to the 9. And they follow an order. And that's one important thing about the sequence of numbers. A finite sequence of numbers is an ordered array or series of numbers. That's the first thing that we talked. The second thing that we talk about, the characteristic of these things here is this one. That they have a kind of a hidden message or that's what we call that the pattern. Or I call that pattern. It means that how they are being generated. And these two are the things that we look at that as in a finite sequence. However, for our lesson, sometimes because we are talking about, but the thing is that we ask ourselves now, you may ask me that, teacher, what's the purpose of taking functions 11 at the high school that we have to talk about just the functions, because we talked about the polynomials, they were functions. We talked about the rational functions. We spent a lot of time talking about, I should say, the trigonometric functions. Then you ask yourself, what is the purpose of talking about the sequences as long as they are not functions? And I'm going to tell you right now, we can say that as a third part of the characteristic of the sequences, it's that they can be represented as a function. They can be represented as a function. Then what do I mean by that? Imagine with the same example which I gave to you, which I had a finite sequence of odd numbers. Imagine that, guys. I tell you that I'm going to create a function which it has a domain. Let's call this domain. And also, it has a range. There are subspaces of, let's say, the real numbers, which will think that any number from the domain can be transformed into a range by a function which provides the means of the transformation. Oh, guys, imagine that. If I say that, for example, the function which I'm going to give you, I'm going to call this. The function is going to be named this. That I say that whatever is this, we call that it becomes 2x. I call that f of x. It becomes 2x plus 1. But the domain which we have, it starts, for example, from all natural numbers plus 0. For example, we have 0, we have 1, we have 2, we have 3, we have 4, we have 5. Correct? Okay. Then we want to make this transformation. What is the transformation of 0 based on that function? You put 0 to the x, becomes what? Becomes 1, huh? What is going to be the transformation of the 1 into that transformation?
3,
3. What about 3?
7,
7. What about 2?
5,
5. What about 4?
9,
9. What about 5?
11.
11. That's so true. And you see, guys, thanks, Rose. You see that if I use this function, which is, I said that whatever I have inside the domain of my function, it transforms it in a way that it multiplies that by 2, then plus it by 1, then you can see apparently that I was able to construct the finite series that I was talking about. Do you see that? How closely they are related? Then you say that if I can specify the domain of my function to be essentially like, if I specify the domain of my function that the domain accepts the value as either 0 and all the natural numbers. By natural numbers, I mean 1, 2, 3, 4, 5, 6, anything. And that's a very important thing, that the domain of the finite sequences should be a natural number. Then you see that the concepts of the finite series and sequences is exactly related to the concepts of the function that we talked. We start with the domain of all the natural numbers with the transformation which acts as a function, and it produces the range, which is the sequence that we see. And that's why we learned that a finite sequence is essentially a type of the function, but with a restriction on its domain. Is it fine with everyone? Did you get the concept?
Yes.
Yes? How about Gloria and Ferris?
Yes.
Yeah? Okay. But there is a kind of, I should say, interesting thing when it comes to the finite series and sequences. And that thing that we're going to talk about it right now is this, essentially, that we say that. We talked about that. We said that, okay, we say that the function that we introduced before, the function that we introduced, it was this. Sorry. We said that the f of x is essentially 2x plus 1. And we said that the domain of the function, it's essentially x belonging to all the natural numbers plus 0, for example. And that was a way that we talked about, we talked about that on our previous example. We said that the function as a way of transformation is expressed as 2x plus 1, But however, we define the range, we define the domain as a restricted domain that it accepts only the natural numbers. Then I was able to define a finite sequence. But there is a minor, I should say, difference in terms of the notation that we use, and we say this as, I should say, in a sequence. We say that instead of writing it like that, we create the series like that. We say that if A represents an element in our finite sequence, for example, look at that. The finite sequence that we had, it was 1, 3, 5, 7 goes to 17. We say that A, it's gonna be a general name of any elements in our sequence. For example, if I say A1, it means that it's gonna be, let's say, the first element. A2 is gonna be the second element. And I'm gonna call this. Then I'm gonna call A sub n this n, which equals to what? Which equals to 2n plus 1. Look at that. That's essentially another way to represent, let's say, for example, to represent a series. And we say that, for example, n belongs to all the natural numbers for our case plus 0. That's another way which is more common to show the sequences and finite sequences and series then. You see, I do not show that. From now on in our class, when it comes to the notation of a finite sequence, we do not represent that explicitly as a function that we talked about that. For example, with the polynomials, with the trigonometric functions. We show them as element-wise. We call that element-wise representation. For example, in our example, what we did, for example, if I put n equals to 0, it means that A0 becomes how much? 1. Means 0, you put n equal to 0. A1 becomes what? It means that I put 1 instead of n. Becomes how much? 2 times 1 plus 1, 3. Thanks. If I put A2 means that I put 2 instead of n. Becomes how much?
5.
5. I say A3 becomes how much?
7.
7. That you put A, 3 to 7 becomes 7. And you say A4 becomes what? You put the 4 inside of the n, then it becomes 9. And also it goes on with any number. Then you see that this expression that we got there, it creates a general term for our finite sequence. We call that the general term. That with any domain, you can completely understand what is going to be the pattern or the finite sequences. And you see that this expression, it is the pattern, the hidden message that we talked about that before. We said that the sequence has an order. It means that the number should be their specified places, and also it has a pattern or a hidden message, which is expressed by that function, which is that general term. And that's what we mean by a pattern. It collects how the numbers are being created. Any questions, guys, so far?
No.
No? Okay. Now, I'm going to give you one example that you make the transformation yourself. Let's see. Okay. Right, how about this one? This starts, I give you one example, two examples essentially. The first one is that I'm going to give you this general expression, an equals to n plus 1 n squared. And also we have the second one. We have Vn, which is going to be 2 divided by n minus 1. Okay, now guys, please, you also try to figure out the number of the terms and write the first 5 elements of each sequence. Just the first 5 elements, okay? Everyone's doing okay?
Yes.
Are you done?
Not yet.
No problem. Guys, please let me know when you're done. Okay, are you done?
Yes.
Yes. Okay, how about Ferris and Gloria?
Not yet.
Not yet. You don't mind if we just we do that together?
Yes.
Awesome. Thanks. Guys, look at that. The first thing which I have to remind you initially is that when you're looking into this kind of, I should say, sequences, the first thing that you notice is this. Look at this. The first term has n at its denominator. Then it means that you cannot put 0 there. Then you have to start by 1 from 1. Because when n is 0, it makes it 1 divided by 0, which it doesn't make sense. You know that the denominator of any fraction should not be 0. It makes it very ugly. Then the thing that we start is this. We say that n plus 1 divided by n squared, n can be any natural number except it should not be 0. Then we start from 1. Then we say that n can take values from 1, 2, 3, and goes all the way. Then for A1, what do we have? We have 1 instead of n. It becomes, the first term becomes what? Becomes 1 plus 1 divided by 1 squared. Becomes how much? Becomes 2. We go for the second term. Everyone can see the color which I'm using?
Yes.
Yeah, awesome. And the second term, what's that gonna happen? It means that wherever we see, because n is gonna be 2, in our expression, wherever we see n, we replace it by 2. We say 2 plus 1 divided by what? Divided by 2 divided by 2. What do I end up with? 3 divided by 4. And you can continue with the rest of the terms. For A3 becomes 3 plus 1 divided by 3 to the power 2 becomes 4 divided by 9. Any questions for this example?
No.
No. Awesome. And now we move on to the next. For the next one, look at this expression. At the denominator, we have what? We have n minus 1, correct? It means that n minus 1 can be anything except that it should not be 0, right? Because it's a rational expression and it has a denominator, and the denominator should not be equal to 0, which means that n should not be equal to 1. Right, guys? Then
Yes.
n cannot be 1. Then you start from the next one. You cannot start from 1 as a natural number. It means that you have to start from number 2. Then we say that we do not have b1. Instead, we start from b2, which becomes what? Becomes wherever I see n, I substitute 2 from it. 2 minus 1 becomes 2 divided by 1, which is 2. Correct, everyone? How about this? We have, I say b3. It means that wherever I see n, I replace it by 2, by 3. Becomes 2 divided by 3 minus 1. Becomes 2 divided by 2, which is plus 1. And you can continue with b4, b5, b6, and so forth. Right, everyone? Any questions?
No.
No, Gloria and Ferris?
No.
Okay. Now, we're just going to give the third example, then we go for the break. Okay, which is a kind of a, the last lesson before we go for the break. It's almost 12. We just solve this example. We have an as a sequence, which is -1 to the power n. Guys, you see this color which I'm writing or no?
Yes.
Okay, thank you. To the 2 to the power n. That's the sequence. An, it's -1 to the power n times 2 to the power n. Guys, please write the first 4 elements of these, the first 5. Sorry, the first 5 elements of this series then. Just the first 5. Okay, is it done now?
Yes.
Okay, how about you, Gloria and Ferris?
Yes.
Okay, thanks. Guys, look at that. There is an interesting thing about this sequence. And essentially, this one is like that. We say that, okay, the first element is going to be for the case when n is equal to what? N is going to be equal to 1. We start from 1. Normally, n starts from 1, 2, 2, 0. 2, 3, 4, 5, anyway. If n is equal to 1, what is going to be the first one? We have a1, the first element becomes -1 to the power 1, 2 to the power 1 becomes what? -2. We have n equals to 2. Then we have a2 equals to -1 to the power 2, 2 to the power 2 becomes how much? Plus 4. Because -1 to the power 2 becomes 1, 2 to the power 2 becomes 4. How about n equal to 3? We have a3, which equals to -1 to the power 3, 2 to the power 3. Becomes how much, guys? -2 to the power 3 becomes -1. 2 to the power 3 becomes 8. Becomes -8. Correct? We have n equals to 4. We have a4 equals to -1 to the power 4, 2 to the power 4. -1 to the power 4 becomes how much?
1.
1. 2 to the power 4 becomes how much?
16.
16. This becomes plus 16. Thank you. And as a last term, we have n equals to 5 then what do we end up with? We end up with A5 equals to minus 1 times to the power 5, 2 to the power 5. Minus 1 to the power 5 becomes how much?
minus 1.
That's right. 2 to the power 5 becomes how much?
32.
Minus 32. So correct. Guys, and now, before we finish, the purpose was that to learn something from this sequence. Look at the sign of each element. What is the sign of A1? What is its sign? Is it positive or negative?
Negative.
That's so true. This is negative. What is the sign of A2? Is it positive or negative?
Positive.
Positive. What is the sign of A3? Is it positive or negative?
Negative.
Negative. What is the sign of A4? Is it positive or negative?
Positive.
How about the sign of N5? Positive or negative?
Negative.
Negative. Guys, look at this. That's from minus positive, positive. Look at that. Minus positive, minus positive, minus positive, and it goes on like that. You see, it alternates the sign between minus to positive and positive to negative. Do you see that? Yeah?
Yes.
And that's why we call these kind of sequences, we call them alternating sequence. That the sign of each element, it just oscillates between minus to positive, positive to minus, minus positive, minus positive, minus positive between each element with the same pattern. We call them alternating sequences. That each element in that series take its own number. Right? Did you got that? Any questions?
No.
No. Guys, if you have no questions, I think that's a good time now we take a break. And now we're going to take a break and let's come back by, let's say, what time is it now? 12:05? By 12:20, please come back by 12:20. Okay?
Okay.
Okay, thanks. See you guys in 12:20 then. Some very small stuff to cover, and we should be done for the lesson for today. And essentially, we're done for almost all the materials that we were supposed to cover for this term. And essentially, nothing is much left. We went in a very fast pace, and we covered many stuff. Okay, now. Guys, look at this one. I'm just going to give you one finite, I should say, sequence. Then I should say we move on to something different. Imagine that. I'm just going to start by writing a finite sequence, and I start by that. I start by the term 1 and 2. And I say the third term, which I'm looking for that, it's going to be, look at that. It's going to be very interesting one. It's going to be this finite sequence is going to be a very interesting one because I do not explicitly gives you the function, the transformation, which you can just deduce from it, the nth term of that sequence. But on the other hand, I tell you, recursively, that's what I tell you why do we call these sequences recursively? Because I tell you that in order to find any elements of that sequence, you have to add the last two elements. For example, for the third element, if you are if the prescription that you have to make the elements of sequence, I tell you for this one, you get the sum of the last two, then becomes 1 plus 2 becomes how much? Becomes 3, right? Because 1 and 2, the last two elements which they stand behind this box, it becomes 3, then it becomes 3. And logically, it's very easy to see that if you want to get the fourth element of the term, you have to add the third and the second element, which is 2 and 3. Then how much is that gonna be then? If you add 3 and 2 together, becomes 5. Because 3 and 2 becomes 5. How about the next element, which is the fifth element of this sequence? Means I have to add 3 and 5 together, then it becomes how much? 8. Then how about this one? If I want to get the sixth element, how much is that going to be then? What's your guess?
13.
13. How about the next elements?
21.
21. Thank you. And we can go on and on. But now, guys, look at that. Now I have a finite, presumably, I have a finite sequence. If you remember from the thing that we covered before we go for our, I should say, before we go for our break, we said that for a finite sequence, we have two elements. The first element of these ones is going to be, the characteristic is going to be the elements, they should just stand in order, and also they follow a pattern, which that pattern as a hidden message follows a function. And now, can you, by guess, as I mentioned that to you, guess what is going to be the hidden message of these finite sequence elements? What is that going to be? If I just want to write AN as a general term, which represents the pattern of this finite sequence, how can I write it? We know that we have to add the last two elements before AN. It means that the elements before AN, what is that? AN minus 1, correct? Plus the element before AN minus 1, because N minus 2. And that becomes essentially the hidden message of this finite sequence that we talked. It's very easy. It's very easy to catch up with it, because we will see that the AN, always we call the AN as a general elements for our finite sequences. Our finite sequence, the general element, as we talked about that, verbally we said that you have to add two last elements. The element before AN is A minus 1, and the one before that is N minus 2. That's right? And in case if you have some, I should say, some still questions that how did I possibly can just find elements, I'm going to show that to you on this axis. Guys, imagine that. I'm just going to start at the middle of a sequence. I call that element AN. AN is a sequence, an element of my sequence. The next element, how should I call it? AN plus 1. The next elements of that sequence, how should I call that one? AN plus 2. How about the last elements? AN plus 3. and move, I go on. But I'm going to move to the left. Before that elements, how the elements are going to be represented. To the left side of the AN, it becomes AN minus 1. Two elements before that becomes AN minus 2. And the other one becomes what? AN minus 3. You see that what happened? But AN, this one was essentially my reference element. I call that the reference element. Elements afterwards, elements in front of the AN, and elements backwards on the back side of the AN is going to be represented like that. Correct, guys?
Yes.
Yeah? That's what we call these elements, this series, recursive elements. Let me write it. Recursive sequences. By a recursive sequence, I mean something like that. In a way that, for example, by this sequence, we call these one recursive sequences because they are recursive, because in a way they should be called recursive because in order to find any elements of that order, in order to find any elements of that sequence, we need the elements before that sequence. Of course, we cannot find the elements. We cannot express that in terms of the elements which comes after because we cannot still know what's going to happen. But sometimes we can construct our sequences in a way that each element is defined as a function of the element before that. For example, you can say the last two elements, they're going to be summed up. Or you can find out recursive elements as an example, as another example. I'm going to show you this example that, for example, you define a recursive element and you say that, for example, I'm going to define it in a way that I say that each element AN is represented as, let's say, for example, square root. I'm going to make it very crazy. Square root of 4 times of cosine of AN minus 1. But you have to also compose something as a restriction. You see, it can be even that crazy that you take the square root of 4 times of the cosine of the element which is behind the AN. Then you see that in order to go to the next step, you have to make the step before you. You are at the 21 element, you have made your 20 elements. In order to go to the 22nd element, you have to work with the 21st element. You see, each element is constructed as a function of the prior elements. And that's why we call that recursive sequences. Does it make sense, everyone?
Yes.
Yes, any questions?
No.
No. Okay, now. Let's go to the next page. Let me see if I can give you an example before we move on. Okay, before we move on, let me give you an example of what do we mean essentially by the recursive elements, and you solve it, and then we should feel more comfortable. Okay, now I'm going to give you an example as a recursive element. I'm going to define the recursive element like that. I'm going to say AN is going to be defined in a way that you have to take AN minus 1 plus AN minus 2 But everything should go to the power 2 for the second element. Okay, guys, everyone can see this sequence? You can see what I have written?
Yes.
Yeah? Look at that. What do we say? We say that each element, an, it's equal to its previous element plus the previous element of the previous element. That one goes to the square 2. Can you please write the first 5 elements? The first 5 elements. Can you do that?
Yes.
Oh, you can do that, Rose? That's great. What is the first element? Rose, Gloria, and Ferris. Look at that. It's impossible to start. You know what? Because we said that in order to find element n, we need to know the prior 2 elements. We know n can be 1, it can be 2, n can be anything, but we do not know what is the first 2 elements. You see, if we have 2 elements, we can get the third element. But what are the first 2 elements of that sequence? Do we know that, Rose?
Rose, 你听懂了吗?
What, Ferris?
No, I just asked, did Rose understand that or not? Because like I didn't understand it.
Okay, then I say that, look at Ferris. I say that, for example, but that's a good thing, Ferris, for you because you are not doing any trigonometry. By the way, did you get the chance to watch those videos to catch up with the inverse of the trigonometric function?
Pardon?
Did you get the chance to watch those videos?
Yes, I watched it.
Awesome. We have enough time. We have almost over a week. And if you plan to just watch a video per day, then you are going to be in a good position then. But this one, how about this? I say that, for example, guys, I'm looking for example, element number 3. In order to get the element number 3 of this finite sequence, I need to know element number 1, element number 2, and element number 1. Why? Because imagine that. I put n equal to 3. I say A3 equals to A 3 minus 1 becomes what? 2 plus A, and instead of n, I put 3. 3 minus 2 becomes what? Becomes 1, which means element number 1, which it goes to the power 2. Look at this one, guys. I have element number 3, which is expressed in terms of, Ferris, you listen?
Yes.
Awesome. Look at that. I have element number 3 in case when I put n equal to 3. Means when n equals to 3, I have element number 3 expressed in terms of element number 2 plus element number 1 to the power 2. But what is element number 2? Element number 2, you may ask yourself, element number 2 is going to be this. You say, no problem. You're looking for element number 2. I can give you element number 2 because I can say that I put n equal to 2, then it becomes A2. It follows from the same pattern. Becomes A2 minus 1 becomes what? 1 plus A2 minus 2. 2 minus 2 becomes what, guys? 0, huh? A0 to the power 2. You ask yourself, what is A1 then? You say, okay, in order to get the A1, I again go back to the same prescription. I say the A1 is going to be what? I put 1 is for n, then I have A0 plus A 1 minus 2. 1 minus 2 becomes how much? Minus 1, huh? Minus 1 to the power 2. Everyone is okay so far?
Yes.
Yes? Look at these guys. We started from element number 3 because we know that the sum of the last two elements gives the forward element. But for element number 3, we need element number 2 and element number 1. We use the same prescription to get element number 2 and element number 1. For element number 2, we saw that we need element number 1 because we have A1 plus A0 to the power 2. In order to get element number 1, we get A0 plus A minus 1. And you see that here you need element number 0. And in order to get element number 0, what's happening? You say, okay, I'm going to put 0 there. And it becomes A0 minus 1 becomes minus 1 plus A minus 2 to the power 2. You see that? You come to answer it yourself. What is element A? 0, you have to find element A minus 1. And you have to put what? To get n equals to minus 1, which is not acceptable. Because we learned that n, the number of the elements, n represents what, guys? If you remember, we said n represents the number of elements. Then it doesn't mean that, for example, if someone asks me, how many students you have in your class? I come, wait a minute, I have minus 3 students. Does it make sense?
No.
No. Then as a result, it doesn't make sense that we have the number of elements of a finite sequence that becomes minus. Huh? It doesn't make sense at all. Then as a result, what do we need to do? The thing that we have to need to do is that we say that we cannot have n equals to minus. Then we see that we cannot construct the first two elements. Because in order to find the A2, we needed to know A1. In order to know the A1, we needed to know the A0. Then in order to know the A0, we needed to do A minus 1. And it goes on to minus infinity. Then you say that we cannot proceed further. Then this method is not going to be acceptable because it leads to nowhere and it doesn't make sense at all. Then what I'm going to do is that I come to cross these elements. I say I cannot proceed any further. You see that, guys? Then as a result, in order to write the sequences of these sequence with its hidden message, which is there as a function, we cannot start. It's as if you just want to run your car. You want to drive your car, but there is no gas in there. The car doesn't move. Because these first two elements, they were so crucial to start with. If I do not have A2 and A1, I cannot start the engine and I cannot drive the car because it leads me to nowhere. It gets me to write the elements of n minus, for example, 1, which it doesn't make sense. As it doesn't make sense, I have minus 3 students in the class. Then in order to not get stuck with these recursive sequences, remember, we call them recursive sequence because the function or the hidden message which it asks you to start the sequence is dependent on the prior elements of the sequence. Then you see that with the recursive sequences, we need to know what are the first two elements in order to start the engine. And it's like that. You want to drive the car. You need to have some gas initially in the tank. Is it correct, Rose, Faris, and Gloria? Yes? You need to have some gas inside the tank to start the car, then drive the car. And it's going to be like that. I'm just going to start this recursive series once again. And I say that an equals to an minus 1 plus an minus 2 squared. This is the same recursive series which I have, sequence which I have. However, this is the car, the brand new car, which you bought, and I fill the tank with some initial gas for you that it enables you to drive. Imagine if I say A1 is gonna be 1 and A2 is gonna be 2. We call that starting elements. I call that the gas on a brand new car. Then you can move on. Then you come here to say what? You come here to say that, okay, my third element, which I was talking about that, my third element is gonna be n is equal to 3, then it means that if you put, becomes A2 plus A1 squared, which is essentially becomes how much? What is your A2? It's 2 plus 1 squared. It becomes 3. Does it make sense, everyone?
Yes.
Thanks, Rose. How about Faris and Gloria?
Yeah.
Yes? Fantastic, guys. And now, please, continue with the elements number 4 and element number 5 and element number 6. Then we continue that. Okay. Guys, what has happened to Philip? He doesn't show up. Guys, are you done now?
Yes.
Yes. How about Ferris and Gloria?
Wait a minute.
Okay. Okay, let's do that together. And you come to say that, okay, now we want to construct A4. I do the A4 and A5 and do the rest of it yourself. A4 means the case that you put n equal to 4, which represents your sequence as A3 plus the elements before that, which is A2 squared. How much is your A3, elements number 3? We cut it at the previous step, which is 3, plus your second element, A2. How much is that? 2. We were given that as an initial gas in the tank of your car. Becomes 2 to the power 2. Becomes 3 plus 4 becomes how much? 7. Ferris, are you okay? Gloria, are you okay with this method? Yes? Now, with the last elements, which I'm going to do, is going to be with the elements number 5. We call for element number 5, we say that it means that the n, the number of the elements, is going to be 5. Then it means that you plug in the 5 in for the n. Then we get what? We get A4, which is the prior elements, plus it becomes A. When you put 5 and becomes 3 to the power what? 2. How much is my A4? I got it at the previous step. It was 7 plus. How much is my A3? It is 3. I got it previously to the power 2. Becomes 7 plus 9 becomes how much? 16. And you can continue like that. That's what we call the recursive series, and always they need some initial, they call that starting seeds, starting elements as a tank, as an initial gas in your tank to continue and move on. Any questions, guys?
No.
No? Okay. Okay, what time is it now? It's almost 1. We have to stop now, and but before we move on, everyone is there before we leave the class?
Yes.
Guys, we have one thing to do. We have tomorrow, we have 2 presentations. We have to only 1. I have to ask one of you, please put your presentation on Friday. Who wants to do the presentation on Friday?
It's okay for same thing for me for tomorrow or Friday. I think.
Okay, can you then do that tomorrow, Ferris?
Yes.
And Gloria, can you do that on Friday?
Yes.
Awesome. Then guys, actually the class is done now. Thank you very much for your attendance and being active in the class. Tomorrow start the session with the new easy stuff, because the things is going to be very easy and cool. Before the exam, we're going to take it cool, take a deep breath. We're going to be very slow, moving very slow then. Then if you have no questions, I hope that you have a very nice day, and see you all tomorrow. And bye, everyone.
Bye. See you tomorrow.
Bye, Rose. See you tomorrow.